Alright, so in the last video we solved for this truss, we solved for the reaction forces. We got none in the x direction, because there wasn't any x direction forces, no horizontal forces, but we did get 225 and 720 for the two upward forces that each support there. Now what we're going to try to do is find the actual member forces in this truss. So first thing, I want to start, kind of have a picture of the truss here. I want to draw in the member forces at each location. So at point A, is the A down the corner? No, A was at the top. Right? So this is A, this was B, and this was C, and I think I called this D. So at B, I'm going to assume tension in all of these, and if I'm wrong, no big deal. I'll get a negative number, then I know it's actually in compression. So I'm assuming tension, so I'm drawing the forces outward from each point. If you think, oh, why is it pushing in? It's in tension. This is the force on the joint, not the force on the member. It's a reaction force, but it's equal and opposite. So think of your arm in tension. If you were pulling away from your shoulder, there'd be a force outward on your shoulder. Same thing here. If the member is in tension, there's a force outward on that joint. All right, so we have kind of what we're thinking here. This would be the force FAB. This would also be FAB. Order doesn't matter. FAB, FBA, same thing. This is FBD. This is also FBD. This would be FAD. This is also FAD. And this is FAC. FAC. And these two down here would be FCD and FCD. Okay, so our diagram's getting a little crowded. We need to take a look at one of these at a time. So if we do that, I'm going to start, just go left to right, I'm going to start at joint B, just so I can keep track of things. I like to label what I'm doing. So, at joint B, again, at each joint, it's in static equilibrium. All the forces should balance out. So, some of the forces in the x should equal 0. Well, let's look at the forces in the x for joint B, and I'm just looking at that part only right now. Alright, so at joint B, I have, with this going on, I have FAB coming up at an angle, FAB, and I have FBD coming straight out, and I have that support force that we already solved for in the last video, 225 pounds. Okay, so let's see what we can do here. I have, for the forces in the x, I have FAB, but not all of FAB. FAB in the x direction, that x component of that, plus FBD equals 0. Now I can't solve for FABX yet, because I don't know what FAB is. So I'm going to move on to the y's for a second. Some of the force of x and some of the forces in the y direction have to equal 0. Flip that to the other side. So here I have 225 pulling up, plus in the same direction, even though it's probably actually not in the same direction, but that's okay. FAB in the y direction, the y component of that. All of that has to equal 0. Well, the problem is we need to get the components for y. And we can do that because we have the dimensions in the truss. That's a nice part about geometry. When it works for one thing, the same proportion still exists for other vectors in the same relationship. So we have, I'm going to redraw this triangle, and since it's part of the truss, and the truss is in black, I'm going to redraw that in black. I like to color coordinate. This side was 12 feet, this side was 8. And we're actually looking at that angle. That angle theta is actually this angle theta in the diagram. So if that's true, and we were looking at the forces along here, if that was what did I say? FAB, right? Then FABX is in that direction, and FABY would be in the vertical, the opposite side. So the adjacent side, really the cosine between this, the adjacent side deals with cosine. So the cosine of that angle, cosine of that angle is the FABX over FAB. Now, we can work backwards and do inverse tangent to find the 12 foot and 8 foot, or I could just use the 12 foot and 8 foot to find what that hypotenuse is using Pythagorean theorem, and then skip the angle altogether. I usually do that. I'm going to do it the other way just for kicks because I don't usually show that, but let's find the angle first. If I wanted to know what that angle theta is, let's see, tangent of that angle, of angle CBD, right, which I'm calling theta, tangent of that would be opposite over adjacent, so that would be 8 feet over 12 feet, right, so that angle would be the inverse tangent of 8 over 12 or 2/3. So grab my handy dandy calculator, take 2/3, 0.6 repeating. Usually this might be a shift or a second, usually above the tangent, the tan minus 1. Inverse tangent, this angle turns out to be about 33.69 degrees. So if we know that, and I rearrange our equation over here, FABX equals FAB times the cosine of our angle theta. So FABX I'm actually going to tell you what, I'm going to take this, plug it back into, I'm sorry, that would be that component right there. We were wanting the y we set up for this equation, and I went in a separate direction. But that's okay, we'll need that in a second. So if the cosine is going to give us the x direction, the sine of that angle is going to give us FAB y over FAB, because that's the opposite over hypotenuse. The hypotenuse is FAB. And we know the angle, so we plug back this guy back into there. And I'm quickly running out of room, but that's okay, we can make it work. I'm actually going to plug that back in down here and say 225 plus FAB sine of, what did I say, 33.69 degrees. All of that should still equal 0. So now, I'm going to have some room over here, so I'm going to come over here. If you can follow me as we do this, that'd be great. I have FAB sine of 33.69 degrees equals a negative 225. I just brought that to the other side. Divide by the sine of 33.69 degrees. Divide both sides by that. I get FAB equal to 225, or rather negative 225, don't forget that. And the sine of 33.69 degrees is 0.55. So FAB divided by the 225 equals 405.6 pounds. Alright, so that's my FAB. It's my first member. Got my first member. So, and just double check the math real quick. Make sure I didn't make any mistakes or put anything in the wrong place. I think that makes sense. So I have FAB equals 405.6 pounds. Oh, I forgot the negative. It was negative 225 up here. I almost forgot the negative. So that means it actually wasn't in tension. This is actually in compression. I always assume tension, negatives mean it's in compression. Alright, so I have FAB. So now I could find FABX and solve for FBD. So I'm going to do that. And I'm going to make some room for myself down here. Well, actually, I'll take that back. I'll put it on the next page, just so we can follow what's going where. I'll plug the FABX back into over here on the new page. So I get rid of my eraser. I had FABX plus FBD equals 0. But FABX is really FAB cosine of theta, right? Plus FBD equals 0. Now FAB we just said was 405.6 pounds, and that's the cosine of 33.69 degrees equals a, move this over to the other side, negative FBD. Oh, this was also a negative 405 as well, so you can't forget that. I've got to keep that with it. So if I grab a calculator, 33.69, the cosine of 33.69 is about 0.646 times 405. Oops. .69 cosine of that is 0.832 times 405.6 equals 337.5 pounds for FBD. Great, alright, so I can go back one slide. Usually you can just do that. Back one slide. There we go. Alright, so when I was over here, I'm going to check one thing real quick. Yeah, okay. So now I have FBD, we said was whatever it was in the next page. So I have FAB, I have FBD. I'm going to move on to joint D, which has FBD, FCD, and FAD all in one, but it's a fairly simple joint. So I'll go back to the next slide and separate all of this out. So joint D, and if you had this all in one page, it'd be much easier to see, but I don't, so we're going to deal with it. But this one was the one in the middle. So I had FBD over here. I have FCD over here. And I have FAD over there. Now you can see right away that some of the forces in the y direction have to equal 0. Well, there's only one force in the y direction, FAD. So that has to equal 0. Awesome. One of them done. And some of the forces in the x direction have to equal 0. Well, we have FBD going left. We have FCD going right. So guess what? They have to balance each other out. They got to be equal. So if FBD is 337.5 pounds, then FCD is equals FCD. FCD is 337.5 pounds. Alright, got that one. So we have FBD. If I go back a slide again. I have solved for FCD. I've solved for FBD. I've solved for FAB. I know those. I've solved for FAD, which is 0. So I have one left. And up at the top, joint A, that's kind of complicated because I have two forces on an angle. I'm going to go to joint C to get that last part, the FAC, right in there. So we had 720 pushing up from it, FCD pulling to the left, FAC going up at an angle. So I just kind of got to remember that when I jump to the next page. But again, you probably would have this all on one page, nicely written out, very organizedly. And alright, so joint C. We had one there. And color coordinate again, of course, have to always. We have FAC. We have FBD. We also had one support force coming up from the bottom, 720 pounds. Okay. So I'm going to look at the forces in the Y, only because we're only going to need to do one of those. We only have one equation to solve for here. So sum of the forces in the Y direction equals 0. I have 720 going upwards. And I also have the Y component of FAC. FAC in the Y direction has to equal 0. So now I need to look at that angle right there, which I don't know what that is. So but we can figure it out. If I go back to the truss, that side of the angle is a little skinnier. It was 3.75 by 8 feet or 12 feet. Now I don't remember, so I should take a look before I do it wrong. It was 8 feet tall, right? So it was this triangle right on the right side of there. It was 8 feet tall and 3.75 feet wide. Excellent. So this was 8 feet, and we want that angle right there. So if we want FACY in the Y direction, that's going to be the opposite side. Let's throw this toolbox over here on the right. Keep it there. We want that vertical direction, so that side, our opposite side. If we're thinking opposite, we need to think sine. So let's work backwards to find the angle first. The tangent of that angle would be opposite over adjacent, so 8 feet over 3.75. So again, the angle theta in this case, actually I should call this something different. I'll call that angle phi. It's already called the other one theta, so we don't get them too confused. Angle phi, angle phi. Alright, so phi is the inverse tangent of 8 over 3.75. Nasty looking fraction, but that's what we have calculators for. 8 divided by 3.75 equals 2.13. Repeating, inverse tangent of that is an angle of 64.88. Throw a 5 on the end, what the heck. 85 degrees. So now I have that angle. I want FACY, that's this opposite here, and that's the opposite side. So 720 pounds plus the upward direction of that, since it's going upward, would be FAC, the hypotenuse, times the sine of phi equals 0. Right? Because just to be clear, the sine of phi would be opposite, which would be the 8, or the FACY over the hypotenuse, which would be FAC. So if I solve for FACY, I get FAC times the sine of phi. So again, 720 pounds. And I'm going to go ahead and throw this to the other side. Equals a negative FAC Actually, you should throw the other side. Would make more sense. So back that up a second. Have FAC times the sine of 64.885 degrees, which is 0.905 or so. I'm going to leave that in my calculator so I can use it later. Throw the 720 over to the other side. So FAC equals 720 divided by 0.95, which gives me, drum roll please, 795.2 pounds of, let's see, that would be negative, so it's actually in compression. Which kind of makes sense. The truss we were looking at was pushing downward, had a force pushing downward on it, so it makes sense that that was that those two members on the outsides are both in compression. Okay, so just to summarize, let's see, FAB was 405, FBD was on the next page, FAD was 0, FAC was on that next page. So if I go to, I want to just redraw the truss, just so it's nice, neat, and clean as to what we got. Draw this. We had support forces. This was 720 pounds. This was 225 pounds. Leave some space to write what these are. So I believe this one was 337.5 pounds. This is also the same, 337.5 pounds. This is in tension. This is in tension. All right, I'll put the red for compression. This was, middle one was 0. There's no tension or compression on that. And this one we just solved for, I believe, was, still in the calculator, 795.2 pounds of compression, and this was 405.6 pounds of compression. Oh, and there was the original 945 up here. Pounds. Everything's in pounds. Pounds, pounds, pounds. And that, ladies and gents, is a solved truss, top to bottom, all the way to the bitter end. If you've made it all the way through, all 30 slides of this, all up-teen videos of whatever that is,